So I see we've hit a cool 100 participants, 101 as I speak. Very nice. Hello again. I'm Adam Chapala, Jason's PhD advisor. We also have here, as the other members of his thesis committee, Nikolai Zeldovich, who is hosting this Zoom meeting, and Samana Marasinghe. I think we should probably get started now. I'll do the customary introduction of the defendee, whatever the right word is. I had the pleasure of first meeting Jason as an undergraduate researcher in a project that actually my colleague David Spivak recruited him for, and I'm glad to see David's here on this call. We were doing really mathy stuff with category theory, but using computer theorem proving. And over the years, it's been my pleasure to watch Jason develop from his background in math and physics to pick up more and more of the tools of the trade of computer science implementers. In particular, we've done a lot under the heading of compilers, which is a kind of tool for building software. And I thought it would be nice to start with a graph representation of Jason's progress over the years. So let me try to do that with screen share now. Right. I wonder if this is going to work. Actually, I better start this presentation first and then screen share. Okay. Right, so I hope everyone can see a nice little graph here. And for those of you especially who are familiar with Zoom, I will invite you to use the text chat to try to guess what I'm graphing here, especially people who don't already know the answer. I've talked to some of you about this in advance. Okay, someone guesses git commits. That's quite relevant here, not quite right. And someone else guessed Coq bugs, errors he spotted. That's exactly it. So this is a graph of all the issues in the Coq bug tracker. Coq is this system we use for machine check mathematical proofs. And there are forms that people have used over the years to go and report issues that have appeared in it. There's a little imprecision here. These results are thanks to methodology suggested by Mathieu Souzeau, who I think is also on the call and is one of the Coq developers. Let me fill in a little more information here. This is, I don't know which of my windows are blocking what everyone else can see. Someone can't see anything being shared. I think a lot of people see it. Sorry for those who might not be able to see it. I'm not sure why that would be. This is like all the issues anyone has reported in this system in each of these calendar years. And then there's Jason's amount in there. So he's varying across the years, but 2016 apparently was quite an impressive year, 2014 as well. Though honestly, I'm told before 2017, these are kind of approximate. They can't, after that point, they switched to GitHub and we know exactly who reported each issue. Anyway, we can still plot the fraction of all the Coq issues that were attributed to Jason over the years. And I think the fact that it's going down is because of a change in software, not because Jason has dramatically ramped down his level of gremlin nature in finding issues in Coq. So which of these were fixed? Yeah, good question. I'm trying to remember. I decided to simplify the graph here, but it was at least half of them are fixed on average over time, I think. Jason probably has a better idea than that. Jason, do you remember what fraction of your issues are fixed in general?
I do not. Okay. I know that some of them tend to be fixed very quickly within a couple days, and others I think are still open from the first year of my PhD. But
got it. Okay.
About half sounds at least within the right order of magnitude.
Fair enough. So I think sort of what we're seeing on this graph at one level, Jason progressing from the point of roughly never having taken a computer science class to being an expert on issues ranging from type theory to compilers and all the pragmatics of the Coq system itself. And so I think now, I'll stop sharing, we are going to have the chance to hear about some of the details of the wizardry he's been participating in over this time. And so I don't think I'll delay any further and let Jason start his presentation.
Thanks, Adam. Let me throw up my screen share. Okay. Good morning, everyone. I would like to start with some belated Thanksgiving toasts. Sorry, I need to be able to change my, right. First, thank you, Adam, for your introduction, for all of your support and guidance and encouragement through the years. I obviously don't know what it would be like to have any other PhD advisor, but I can't imagine having a PhD advisor who would have been better for my mental health in my PhD than you. I want to thank my coworkers, with special thanks to you, Andres, for many engaging conversations and rich and productive collaborations. Mom, thank you for taking every opportunity to enrich my life from my very earliest years and setting me on this path. Thank you, Rachel and Dad and the rest of my family. You've always been kind and supportive. And thank you to the several teachers in this audience from my 24 years of education for inspiring me and nourishing me. Thank you, Allison, for your friendship through the many years. And thank you, Raji, for your faith in me and for everything you've done to help me excel. And finally, thank you to everyone who's made the time to be here, for your support and for your interest. I will be defending my thesis titled Performance Engineering of Proof-Based Software Systems at Scale. The things I want you to take away from this talk are that there's an opportunity to automate verification to enable innovation. The big problem in automating verification in interactive theorem provers is asymptotic performance. I will talk about my contribution to solving this problem through my work in reflective partial evaluation, and I'll conclude with what I see as important next steps for the field of verification. The context of this talk will be the project Fiat Crypto, where crypto here is cryptography, not Dogecoin. Fiat Crypto is joint work with Andres, Jade, and Adam. And the code that we generate is now used in a majority of secure connections from web browsers. Our code implements the elliptic curve cryptography underneath HTTPS, which is used wherever you see that secure lock icon. Our code is used in Chrome and Firefox, in the Go standard library, in Facebook's LibreCoin, in WireGuard in the Linux kernel. And it was picked up just 3 years after we started working on it, which is highly atypical for academic formal verification projects. I believe a large part of this is the way that Fiat Crypto enables developers to more quickly and confidently innovate using crypto. In crypto, there's often a small mathematical specification, such as multiply two numbers and reduce modulo a prime. In elliptic curve cryptography, there are many long and complicated implementations of the spec for reasons of security and performance. There's good reason to innovate here. As computers get more powerful and attackers have access to more computational power, we need to improve the mathematical security of our crypto. Additionally, we can reduce costs, both server-side and user-side, by optimizing the implementations of our crypto. However, these optimizations complicate the code, and because the implementation is so far from the specification, there's a lot of room for error. Such errors have an enormous cost because attackers have financial incentive to exploit any bugs. And since it's so hard to find the errors, even billions of random tests are generally not sufficient. There's an attitude of don't touch it, it works, even when this gets in the way of innovation. Verification can fix this. People, represented by Lightbulb Man over here, can write proofs that the code matches the spec. And these proofs will potentially let us deploy new crypto with confidence by virtually eliminating the possibility of bugs in the code. The problem is that there's a 10x to 100x overhead in the lines of code of verification over the lines of code being verified. Here you can see the numbers for some successful verification projects. And what this overhead means is that when you want to verify a modest program, you need to put in an enormous amount of effort for the verification. Automating verification can fix this problem. One way of automating verification is for Lightbulb Man here to write a script that generates both the code to be verified and the proof that this code matches the spec. In this way, when we have many related specifications, as we do in elliptic curve cryptography, we can write just one script parameterized over the differences in the specification and thereby pay the upfront cost once and get the verification of a significantly larger amount of code for free. And this allows us to significantly reduce the marginal cost of verifying new code. Our script is run and checked by a dependently typed interactive tactic-driven proof assistant, in this case, Calc. And in this context, dependently typed proof assistants are expressive, interactivity allows easy insertion of human ingenuity, and tactics allow the aforementioned automation of verification. The big problem here in automating verification is what I'm going to talk about now. Lightbulb Man writing the script removes the overhead of writing things over and over, but running the script in the proof assistant still takes too long. The big problem is asymptotic performance. We can automate toy examples in the proof engine. We can automate their verification. But this automation takes way too long when you try to run them on real examples. As you see in this plot, in an earlier version of fiat crypto, the automated verification that worked fine on an example of size 2, taking about 17 seconds, on an example of size 17 was projected to take over 4,000 millennia. 4,000 millennia is way too long to wait. And the size here is measured in the number of machine integers that are used to represent a single big integer that you might be multiplying in cryptography. And the standard name for this is limbs. So you would say an example of size 2 is using 2 limbs. In size 17, you're using 17 limbs. My work has been about fixing this performance problem. And by the way, none of the performance issues in this talk are about brute force search. They're all about manipulating expressions. After integrating my contribution into fiat crypto, we're able to generate hundreds of thousands of lines of verified code without needing to do any marginal work. This means that engineers who want to innovate with different crypto parameters can deploy verified code with ease. We're turning engineers into lightbulb men. The code that we wrote makes a pretty cool tool that can be run on the command line. Here you see an invocation of our command line binary, where you pass it a description of the curve, the machine architecture, how many bits your machine can handle, some other curve parameters, and the prime number you want to reduce modulo. And in just fractions of a second or a couple seconds or occasionally a couple minutes for the very large prime, it generates this enormous amount of verified C code that you really wouldn't want to have to write by hand or verify by hand. And I think the ease with which our tool can be used to generate code contributed significantly to its adoption in industry. Here you see it took about half a second to generate that code. The rest of this talk is about the work that went into making fiat crypto. If you came here just to support me, you're now welcome to go to sleep, and I'll let you know when you can wake up. So the requirements for fiat crypto were that the code that we generate must be fast and constant time. Fast for server load, constant time for security. It should be easy to add and prove a new algorithm, new prime, new architecture. This is what enables innovation. And finally, the verification should not run forever. 4,000 millennia is way too long. If the verification doesn't finish in reasonable time, it's not actually useful for anything. Where was the asymptotic performance issue? In fiat crypto, we carved the low-level code up into these neatly separated, conceptually distinct units that you see on the screen. And these are small enough, mostly, to not hit asymptotic issues during interactive verification, during running automated verification. And I want to note here that while abstraction is widely used to manage conceptual burden, we use it additionally here to reduce burden on the proof assistant. And while this is not a way that I've seen abstraction being talked about anywhere in the literature, and I think it's very important, this part of the approach is not the focus of this talk. You can see my dissertation for more details. My colleagues worked on most of the individual pieces, and I helped them see how abstraction impacts the performance of running the proof script. I worked primarily on the 2 compilation stages on the far right, and these are the pieces where we generate the code from the other pieces. Here you see the areas of the pieces scaled to match the running times of the proof scripts. And this is before I solved the asymptotic performance issue of partial evaluation. This is the running times for 1 limb. On 2 limbs, it looks like this. On 3 limbs, it looks like this. And here, partial evaluation is at almost 2.5 hours and took nearly 60 gigabytes of RAM. I wasn't able to get to 4 limbs because I only have 64 gigabytes of RAM on my machine. And the smallest real-world example that we want to handle has 5 limbs. The largest one that we might want to handle has about 17. The expected asymptotic performance here, I believe, is degree 6 or possibly exponential. 3 points isn't enough to determine that with detail. But let me now tell you what this partial evaluation piece actually is. And I want to note that this one slide, I hope, will be understandable to everyone in my audience. So those of you who went to sleep can briefly wake up. If you have a recipe for making a peanut butter and jelly sandwich that starts with search the house for peanut butter, jelly, and bread, you'll spend a lot of time searching the house every time you want to make a sandwich. This is very inefficient. If instead you always keep the peanut butter and the jelly and the bread in one location, you can instead do the searching while you're writing the recipe. And then you can just write down where to fetch each of these ingredients from. And this will save you a lot of time. Notably, partial evaluation is partial. If you are partially evaluating an equation like x plus 2 plus y minus x plus 6, you can get out y plus 8 without knowing the values of x and y. And those of you who briefly woke up, you can now go back to sleep. I'll let you know when you can wake up again. In fiat cryptography, we use partial evaluation to take template code, of which you can see an example on the left, and turn it into different instantiations of C code. Here on the right, you'll see some very tiny 64-bit code and 32-bit code for squaring a number. The problem with doing partial evaluation is that the tools that the proof engine, the tools that Calc or other interactive dependently typed tactic-driven proof systems give you to do partial evaluation are slow. And I want to note here that we need to do arithmetic or equational simplification. And that's part of why we need to be using partial evaluation in the proof engine with these tactics, rewriting for doing code transformations and not just something called reduction. And rewrite strat and setoid rewrite are the two main tactics that Calc gives us for these partial evaluation code transformations. And the top-down and bottom-up strategies for rewrite strat perform almost identically. Here you see these cubic curves for both of these tactics, or all of these tactics. And the important scaling factor here is the number of binders. This is roughly how many variables you have in a single function, or how many arguments each function takes, or how many variables you have in your context. For the smallest real-world example that we want to handle, we have about 90 binders in the output code. For the largest, or one of the large ones that we want to handle, we have about 900. While the scaling might be OK for 90, it's completely unacceptable for 900. A large part of my PhD work was making this step possible in a way that scales. Let me tell you what a proof engine is now, because I've been using this word a little bit. A proof engine lets you declare a goal to prove and issue instructions to make partial progress on proving this goal. And this is an interactive process that lets you insert ingenuity. You can write scripts to automate the issuing of instructions, and the proof engine will track the progress and the current state. It can then issue a trail, a proof certificate, to be checked by a small checker, also called a kernel. And this is what lets you trust the proof and trust that the code matches the specification. Let me tell you our approach to solving performance issues. We dig deep to find the places where there's asymptotic blowup, and then understand very precisely what the source of this blowup is. As we discovered, the key ingredient, the solution in the case of partial evaluation in fiat crypto, was to fuse the various reduction and compiler passes on a deep level. Let me now tell you a little bit more about how partial evaluation works, what we needed to do in fiat crypto. The key parts are beta reduction, iota delta reduction with rewriting, and code sharing preservation. And I'll now tell you what each of these is. Beta reduction is about plugging arguments into function bodies. It's useful for eliminating function call overhead in the generated code. This is important for output code performance. And you see here an example where when you have a function that takes an argument x and returns x plus 5, and you apply this function to 2, beta reduction will give you back the expression 2 plus 5. And one of the interesting choices to make when doing beta reduction is how you handle binders, how you handle arguments to functions. Iota delta reduction with rewriting is useful for pre-computation and eliminating function call overhead. Iota delta reduction is about inlining function bodies and pre-computing the results of case analysis and loops or recursion. Rewriting is about arithmetic or equational simplification. And this arithmetic simplification is necessary for getting the right asymptotics of the generated lines of code in fiat crypto. We have one algorithm where without arithmetic simplification, we generate a quartic number of lines of code, quartic in the number of limbs. And with arithmetic simplification, we generate only a quadratic number of lines of code. And the number of limbs that we're handling is in fact large enough that these asymptotics matter. An example of iota delta reduction is that if you map a function over a concrete list, you want to unroll the loop or the recursion of mapping and do the case analysis on the constructors of the list, and you get a function applied to each concrete element of the list. And I want to note that this leaves over beta redexes. This leaves over opportunities for beta reduction. And without using this with beta reduction, the code size can blow up. Many of these reductions, many of the partial evaluation steps are ones that actually increase code size if you don't do them all in a fused way. And here we start to see where the fusion is important. And finally, code sharing preservation is necessary for avoiding exponential blow up in the size of the generated code. The example here, we use let binders for variable assignment. And when we map a function over a concrete list, if there are some variable assignments in the way, sorry, there's some noise outside that's distracting me a little bit. Okay, so if we map a function over a concrete list and there's binders in the way, there's these let binders in the way, the iota delta reduction or the rewriting patterns won't trigger. And so we really need to move the let binders out of the way in order for it to trigger. And if we were to inline the let binders instead, that would lead to exponential blow up in the generated code size. And note again that here, again, we see in the third reduction step that doing iota delta reduction without having other optimizations, perhaps without rewriting in beta in this case, leads to a blow up in the size of generated code. And so again, the interesting parts are fusing the passes. And I want to note that each of these requirements can be thought of as a kind of compiler pass. There are a couple of extra requirements in the context of fiat crypto, which are that the entire process needs to be verified without extending the trusted code base. And it should be performant. It should not introduce extra superlinear factors. And I want to note that we didn't quite manage not introducing extra superlinear factors. We do a lot better than the interactive solutions, but the primitive step in the proof engine that we use called VM compute, in fact, is already quadratic in the number of binders in output code. But I believe this problem can be fixed separately from this solution. And I want to emphasize again, the compiler passes really need to be fused in this domain. This is needed to achieve adequate asymptotic performance. If you do all of the iota delta, or let's say if you do all of the delta reduction without anything else, you blow up the code size. If you do all of the iota reduction without doing any beta reduction, you blow up the code size. If you do all of the beta reduction without being able to do iota delta reduction, you blow up the code size. If you fail to lift the let binders to expose the right rewriting opportunities, the right reduction opportunities, then the reduction just gets blocked. And again, you blow up the code size. And so we really need to fuse all of these passes to get adequate asymptotics, to not blow up the intermediate code size in a way that results in unacceptable performance. Let me now tell you about the way that I implemented partial evaluation to solve these performance problems. I implemented it reflectively for performance and for verification, and I'll tell you what this means shortly. I used normalization by evaluation, which is a technique that exists in the literature for beta reduction. I rewrote this in a let lifting monad for code sharing preservation and fused it all with rewriting for iota delta reduction with rewriting. Proof by reflection is about using a different sort of step in the proof engine. Most of the steps in the proof engine make partial progress towards proving some goal and leave behind a trail. Coq's proof engine has a highly optimized primitive step for validating the output of a computation. This goes under the name VM compute or native compute. And reflection, proof by reflection, is about phrasing the goal in a way that we can just validate the output of a computation in order to prove the goal. It's really about verifying the process rather than having an ad hoc process that leaves behind a trail. And as an example for reflection, I'm going to talk about proving evenness. So you can have this inductive predicate that defines what it means for a number to be even, saying that 0 is even, and when n is even, 2 plus n is even. And the way the workflow in the proof engine works when you're not proving reflectively is that lightbulb man over here will say, my goal is to prove that 9002 is even. Coq will say, OK, that's a valid goal. Here's your goal. Lightbulb man will write a proof script, for example, repeat constructor. And Coq will spend a long time running it because 9002 is a very big number. It is over 9,000. Eventually, if you don't run out of memory, Coq will say, cool, I've finished. And if you ask it, it'll tell you what the proof is. And there's this enormous proof where you have 4,500 terms, and you repeat this large number in every single term. It's a very big proof term. That's a large part of why it took so long. In fact, it's a quadratically sized proof term. And then lightbulb man says, cool, I'm done. Please check the proof term. And Coq says, great, you have proved that 9002 is even. Note that the time that it takes to run the script scales with the size of the number that you're proving even and scales pretty quickly. And this is, in general, a problem with proof scripts when you have input that scales to be very large. When you want to prove things by reflection, there's a lot more upfront work. Lightbulb man needs to define, for example, a computation that can determine whether or not a number is even or odd. And so you need to define parity. Coq is like, great, I accept that definition. You need to define some helper functions. You need to say, here's my computation that computes the parity of a number. Coq says, cool. You need to prove that when your parity computation says even, in fact, the number is even. Coq accepts your proof. And once you've done all of this upfront work, now the workflow goes much more quickly for proving things. Again, lightbulb man says, my goal is that 9002 is even. Coq says, cool, that's a valid goal. Now lightbulb man says, just reduce this to validating the output of a computation. And Coq says, cool. What you need to do is you need to show me that the output of computing the parity on 9002 gives even. And then lightbulb man says, OK, in this highly optimized proof step, validate that output of the computation. Coq very quickly says, great, I've done it. Here is my proof. Note that this is a very small proof term. And then lightbulb man says, great, I'm done. Please validate the proof. And Coq says, great, the proof works. The reason to use reflective rewriting is that reflective rewriting is asymptotically faster. There are a couple of reasons for this, I believe. One of them is that the trail left by proof engine-based rewriting is super linear in the size of the code being transformed. This could be avoided with a great deal of cleverness. Another reason is that tracking the goal at all when you're doing rewriting incurs superlinear overhead in the number of binders. This one is much harder to avoid. And recursively computing only the output is asymptotically faster. And as a side benefit of doing the entire pipeline reflectively, we can extract it to that OCaml binary that I demoed earlier, and it can be run as that command line utility. Let me now tell you about the other ingredients of my implementation. Normalization by evaluation, which is standard in the literature, is about reusing substitution in Galena in Coq's functional programming language for substitution in a deeply embedded abstract syntax tree. And the reason that we're talking about deeply embedded abstract syntax trees is that when we're doing code generation, we want to operate on a structured representation of the code that we're generating so that we can prove that the transformation preserves the semantics of it. On the slide, everything that's quoted is in this deeply embedded language of abstract syntax trees, and everything not in quotes is in Galena. Here you see already what it looks like to fuse the rewriting with normalization by evaluation. And the transformation that we've done here is that expression application turns into Galena application, abstraction in our abstract syntax tree turns into abstraction in our functional programming language in Galena, and expression constants become rewriter invocations on the Ada expanded forms. In standard NBE, you'd replace this last step with just constant application rather than rewriter invocations. The final step of normalization by evaluation is to do the evaluation, to do the reduction. And here you see that when we do this, all of the beta redx's disappear, and we're left with just these rewriting opportunities with all of the arguments plugged in. And this is important. Being able to delay rewriting like this is useful, and I'll come back to that in a moment. I rewrote normalization by evaluation in a let lifting monad. The let lifting is for code sharing preservation. It brings all of the variable assignments up front. And this monad has assignment and return as the primitive operations, bind as derived. I haven't seen it in the literature how to fuse this with normalization by evaluation, but it's not that tricky. Automatic iota reduction, fusing it with automatic iota reduction, on the other hand, was too tricky for me to figure out. And it wasn't actually necessary for fiat crypto because we only handle a small set of inductive types, things like lists and options and Cartesian products. And so I was able to just hard code the fusion for the particular cases that we needed for fiat crypto. I think it would be interesting to figure out how to fuse iota reduction, case analysis, and recursion or loop unrolling with let lifting in general. Finally, rewriting, which was used for iota delta reduction and rewriting, and the equational and arithmetic simplification, was fused with normalization by evaluation. And here I want to mention that our abstract syntax trees were in parametric higher order abstract syntax, also known as FOAs, where the binders in the object language level, the binders in the abstract syntax tree are represented by binders in Coq's functional language in Galena. And this is a big part of what allows us to delay rewriting in a way that allows us to achieve complete rewriting in a single pass when the rewrite rules form a directed acyclic graph, when there's a standard order that you want to check the rewrite rules in. And the rewriter, the partial evaluator that I wrote, is a very general tool, and it also integrates an extra parameter fuel for when they don't form a directed acyclic graph, and that lets you try the rewriting again when you need to. There are a couple of other features that I want to talk about, a couple of other ingredients that I integrated into the partial evaluator that I wrote. And these were all useful for usability or for performance and for enabling efficiency. We select which rewrite rule to use based on Cox pattern matching so that we don't need to walk the entire list of rewrite rules at every identifier or constant node just to see which ones apply. And we enable this efficiency by on-the-fly emission of a type of codes for the constants that we care about. I haven't seen this done elsewhere in the literature. And finally, we gain another factor of about 2x by partially evaluating the generated rewriter itself using Cox built-in mechanisms for partial evaluation. This adds a little bit more upfront cost, but it seems worth the 2x efficiency on every run that generates the code that we want to generate. And finally, I want to mention that in addition to all of these ingredients, the entire rewriter, the partial evaluator, is parameterized over what rewrite rules you want to use, over what reductions you want to have. And so it's much more general than just fiat crypto. And I also want to note that some of these individual components have been done before. Normalization by evaluation is standard in the literature. There's an existing example in Isabelle Hall where they've fused normalization by evaluation with rewriting, although there it extends the trusted code base a little bit, and they used it only for complete evaluation. They didn't do any examples of partial evaluation. But I want to emphasize that one of the really new things here is fusing all of these compiler passes. In most domains, as I understand it, the compiler passes don't need to be fused. And moreover, reflective procedures can't modularly be fused at a deep level because they live outside the proof engine. And so the work of fusing them and proving the fusion correct needs to be redone from scratch. OK, everyone who I sent to sleep can wake up now. The partial evaluator, the rewriter, it works and it's performant. We see here, again, the graph from earlier, where our approach for doing partial evaluation and rewriting scales well past the 900 binders that we need for P384 and scales well past 6,000 binders. And on fiat crypto, you can see the actual timing of generating some of the curves, some of the code that we're generating. And it scales well past 500, or it scales at least up to the 400, 500 bit primes that we want to handle. This is, even though the times here go up to about 100 seconds or so, this is much, much, much better than the 4,000 millennia that earlier versions of fiat crypto were taking. I think there is not really any comparison. And additionally, I ran into similar performance issues on the project that I worked on for my master's, a parser synthesizer. And I believe that having this rewriter in hand would have solved one of the major performance issues that eventually killed that project. And if I had had it from the start and organized the project around this partial evaluator, I think I might have been able to avoid all of the performance issues. So our approach of digging deep to find the places of asymptotic blowup, understanding exactly the source of this blowup, and then in this case, fusing the different compiler passes deeply to avoid the intermediate code size blowup, worked pretty well. And so we've seen the opportunity to automate verification to enable innovation. We've seen the big problem in interactive proof assistance of asymptotic performance. And we've seen my contribution of reflective partial evaluation. And now I want to turn to what I see as important next steps for the field of verification. Let's take a step back. We succeeded in doing this. We succeeded in making a very useful tool in fiat crypto. But it was very hard. It took a lot of work and effort. And essentially all of the work that I've done on fiat crypto, this isn't literally true, but a significant fraction of it, was to work around inadequate asymptotic performance of the proof engine. Moreover, this is typical. I've probably spent about 80% of the time working in my PhD on working around performance issues in Coq, working on some sort of performance engineering. And our current approach to solving performance issues is to use abstraction to prevent excessive unfolding, to use abstraction with an eye towards managing the performance burden on proof assistance. And again, I haven't seen this elsewhere in the literature, and I think it's a very important tool, but it's not the focus of this talk. And then when we can't handle performance issues by using abstraction, when the pieces are too big, we carve out the proof engine and replace it with reflection. Abstraction alone is not going to be enough. My understanding is that systems code is often written in an adversarial context where you don't get good abstraction. Sometimes the code works around bugs that the people who wrote the hardware aren't going to tell you what the bugs are. And so it's not really possible to make good abstractions. Symmetric crypto code is often written in an empirical fashion, and no one has discovered the good abstractions yet, as I understand it. And performant code often, perhaps always, breaks abstraction barriers. All of these are places where abstraction is not going to fix the asymptotic performance issue. And reflection, I believe, will not save us either. Using a proof assistant is for easily inserting human ingenuity to prove a broad range of things, and using reflection is essentially giving up on the easy part. As the problems get bigger and harder and we need more ingenuity, it won't be cost effective to solve these problems reflectively. Already in the partial evaluator, even when there were essentially only 3 pieces of ingenuity that I was fusing, I hit the same performance scaling issues that I was trying to avoid by writing it in the first place, although the scale was smaller, and so I was able to succeed. This brings up the question, can we avoid carving out the proof engine? To answer this, we need to look at where the performance issue actually is. And it turns out, in my experience, that it's pretty far from the problem that we're solving. This should be obvious in some sense, I claim, in retrospect, because if it wasn't far from the problem we're solving, doing it reflectively wouldn't help at all. And a typical example of this is that this thing that Coq's proof engine does, called EVAR instance allocation, has absolutely nothing to do with the correctness of a given C algorithm. And yet it is the source of the bottleneck in rewrite, in setoid rewrite, in a number of places. In my experience, it's not about generating the proof trail. That's not where the performance issue is. And it's not even really about the individual steps being slow. Most of the time, it seems like it's really about the asymptotics of accessing and updating the data being tracked, and sometimes just walking the term that describes what you're proving repeatedly is too much overhead. Walking the proof term would also be too much overhead. Luckily, Coq does not do that. And I believe that having shared this, I can give an answer of why reflection helped us at all, which is that it's because it's solving a more limited problem. And it allows you to choose your own data structures rather than being tied to the data structures of the proof engine. It allows you to use more efficient algorithms that don't go through the proof engine's way of accessing and updating the data being tracked. And what this means is that writing a proof engine reflectively won't fix the asymptotic performance issue. Moving the entire proof engine to reflection isn't enough. And it's not just an engineering challenge to fix this problem, I believe. Don't make stupid choices isn't enough to get good asymptotic performance. And if you don't believe me on this point, try writing a version of rewrite strat inside a tactic engine where every step can be considered as partial progress towards proving something, and make it linear in the number of binders, the number of rewrite locations, and the size of the term that you're rewriting in, all as additive factors on each other, not as multiplicative factors. This is really hard, possibly even impossible in the current proof engines, in the current kernels. I think that writing this would definitely need changes to Coq's proof engine. It might even need changes to Coq's kernel to support all of these constraints. As a field, we really need to study proof engines with an eye towards asymptotic performance. This brings up next questions about proof engines. I want to share this as a sort of bare bones research agenda. where we start by systematically understanding the field and then asking some deep design questions. Where does the performance overhead really come from? I've looked into where it comes from in the work that I've done, in the projects that I've worked on. And I know that all of my colleagues have at least vaguely similar performance issues. I think it would be interesting to find out as a field if we're all hitting the same performance issues or if we're hitting different performance issues. And in my dissertation, I've sketched out where some of the performance overheads, most of the performance overhead in my projects comes from. I think it's important to ask what things are people currently not doing at all because the performance overhead is too big. And then we can ask, what is an adequate set of primitives for a proof engine to enable people to do everything that they want to do? And what are the acceptable thresholds on asymptotic behavior for these primitives? And then finally, is it possible to achieve adequate performance simultaneously on all of these primitives? Or does achieving adequate performance on one primitive mandate using data structures that are incompatible with adequate performance on another primitive? I think that solving this problem, getting the basics of proof engines right asymptotically, will drastically accelerate the scale of what we as a field can handle and bring verification closer to its promise and potential of enabling innovation in industry. Thank you.